Greetings. So, we will discuss scattering phase shifts and how they are related to the boundary conditions and also to the normalization of the wave function. So, we have seen that a free particle solution has got this general form, the Lth solution for L quantum number, when the potential is 0, which is the case of free particle as a special case of a spherically symmetric potential, and this is the general solution. Now, if V is not equal to 0, you really have a scattering potential, which is the case of interest. Then the solution is exactly like this. It is a sinusoidal function with 1 over r in the denominator. The argument is kr minus L pi by 2 in both cases, except that in this case when Vr is not equal to 0, there is an additional phase shift, okay, and this phase shift is the scattering phase shift, which contains information about the potential. So, let us have a look at this problem, and we look only at the radial part because the angular part solutions we already know, those are the spherical harmonics, and we set up this differential equation for y, where y over r is the radial function. So, with this choice y will need to satisfy a differential equation which is given over here, and if you remove these constants by defining the potential as twice mv over h cross square, you can write it in a form which is rather simple and concise, so that you do not have to write too many constants needlessly. And we will now discuss how the potential Vr produces that phase shift. That is the result that we made use of in our previous class, that the scattering potential generates a phase shift. Today initially we will first demonstrate how the scattering phase shift is produced by the potential, okay. So, the potential that we are going to look at is of this form, that as r tends to infinity, any physical potential will have an influence which will become weaker and weaker as you go farther away from the center of the potential. So, as r tends to infinity in the asymptotic region, the potential will become very weak, and we presume that no matter what is the detailed structure of the scattering potential in the problem of our interest, it is weak enough in the asymptotic region. Now, that is a fairly acceptable assumption. We nevertheless have to discuss by weak what exactly do we mean. Is 1 over r weak enough? Is 1 over r square weak, or is 1 over r cube weak? Okay, these are all weak potentials. They all go to 0 as r tends to infinity, right. 1 over r cube also goes to 0, 1 over r square also goes to 0, 1 over r also goes to 0. Now, are all of these cases admissible in our treatment? The answer is no. And what exactly is this restriction is what I am going to discuss now. So, we will answer this question as to what we mean by the potential being weak in the asymptotic region. So, this is the form of the differential equation that y must satisfy, and assuming that this potential is weak, and we will define what is meant by weakness, the solution will be given by this exponential function multiplied by some other r dependent function, which is represented here by capital F, okay. If this potential was weak enough, so weak that you can pretend that it is simply not there, it is 0, then you have the case of the free particle, right. And in that case the entire r dependence would be contained in this exponential function, e to the plus or minus ikr would be the exact solution. With this potential vanishing, okay, the exact solution would be given by e to the plus or minus ikr, but when this is not completely 0 but only weak, then the function f would not be a constant, it could depend on r, but it would only be weakly dependent on r. Okay. So now we know that when we are dealing with a weak potential, a potential which is weak in the asymptotic region as r tends to infinity, the solution would be given by this exponential function multiplied by a factor which is not a constant, it does depend on r, all the most r dependence is extracted in the e to the ikr function, but the residual r dependence is packed in this function f, which is not quite a constant, but it is not very strongly dependent on r, which means that r changes, the function would change, but not very rapidly, but rather weakly, right. If it is completely independent of r, it would be flat. If you plot it as a function of r, it would be just a horizontal line, that is a function which does not depend on r. If it depends very strongly on r, it will have very many wiggles, ups and downs. If it is only weakly dependent on r, it will have very gentle ripples over a constant line. Okay, that is what is meant by a weakly dependent function. So f is a weakly dependent function of r, it would in fact be a constant if the potential were 0, and this is the case that we are considering. Okay. So now we know something about the function f, that it is a weakly dependent, it does depend on r but only weakly so, and I put the two potentials, there is this real physical potential u which is coming from this real physical potential v, so other than the scale factors 2m over h cross square. So u is the real physical potential, L into L plus 1 over r square is the centrifugal potential which has come from the reduction of the 3-dimensional problem to the 1-dimensional problem. So the 1-dimensional effective potential is ur plus L into L plus 1 by r square, this is the effective potential, and this is the differential equation that we want to solve. What we do know that y can be written as a product of these two functions, and you can take the derivative of y as a product of these two functions of r. So this is what we have got, f is a weakly or a slowly varying function of r. So you can take its first derivative, which is the derivative of a product of these two functions, so it is plus or minus ik f times e to the plus or minus ikr, right, and then you have the derivative of f. Similarly you take the second derivative and you have two terms which are similar, so you can add them together, and after adding these two terms you have got plus or minus twice ik f prime, and these are the three terms that you get for your y double prime. So now you have got the function y expressed in terms of f, you have got y prime and you also have y double prime, and you can put all of them in this differential equation. So let us do that. This is the differential equation, you have got y, you have got y prime and you have got y double prime, and when you put them all together in this differential equation you will discover that f must satisfy a differential equation in which you have put all of these terms, right. It is very simple to do, it is just a matter of simple substitution. Notice that these two terms cancel, this is plus or minus ik square and this is k square. So now you are left with only these three terms in this bracket, and these three terms add up to go to 0. What does it tell us about the ratio of f double prime to f? Because you can divide each of these three terms by the function f. So you have got f double prime by f in the first, you have got f prime over f in the second other than this constant plus or minus twice ik, and then you have got u which I have moved to the right hand side. Okay. Now this is what we have got. Our interest, let me remind you, is in those cases for which f is a slowly varying function of r. What does it mean? If f was completely independent of r, f prime would be 0, df by dr would be 0, right. So f prime is small, it is not 0, but it is small, and f double prime will be smaller still, right. So compared to f, f double prime is ignorable, at least much more ignorable than f prime is. So if you look at the first two terms, the left hand side is a sum of two ratios, one is f prime over f, the second is f double prime over f. But in our case, f is a slowly varying function of r, which makes f prime weak and f double prime weaker still. So the first of these two terms is certainly ignorable compared to the second. Do you recognize the approximation here? Okay. Now when you do that, you can throw off the first term. So for this case, where f is a rather slowly varying function of r, you throw off the first term and you are left with this result. Now you can actually integrate that, because you have got f prime over f and you know what its integral is, right. So you have got f prime over f, which is nearly equal to this plus or minus 1 over 2 I k comes here, and you have got this effective potential, which is the sum of the physical potential plus the centrifugal term. If you integrate this, you get f will be given by e to the power 1 over plus or minus 2 I k and the integral of this effective potential, right. If you have an effective potential, which we know is u plus L into L plus 1 over r square, now we recognize the constraints. If the physical potential was a Coulomb potential, okay, then V would go as 1 over r, u which is proportional to V would also go as 1 over r, and as r tends to infinity, 1 over r plus 1 over r square would go as 1 over r, because 1 over r square goes to 0 much faster than 1 over r does. So the effective potential will go as 1 over r, and the integral that you will need to determine over here will be the integral of 1 over r. Is that right? So if you had a Coulomb potential, which is a common case, which is the case of the hydrogen atom actually, right. If you had a Coulomb potential, you would need the integral of 1 over r, and that would give you a logarithmic function, and you have e to this constant times logarithmic function. And what does it tell us for f? F would not be independent of r. We started by saying that our consideration will be valid for those cases for which the potential is weak, and then f must become only weakly dependent on r, it cannot be dependent on r. But if the potential that we are dealing with is actually a Coulomb potential, we find that f would not be independent of r, okay, which means that this method is not going to work for the Coulomb potential, okay, it does not, but it does work for all potentials which go to 0 as r tends to infinity faster than the Coulomb potential, okay. So that is the condition which is emerging from this analysis. This is the point I wanted to discuss when I said that we are dealing with potentials which fall, whose physical influence falls off in the asymptotic region, but at what rate it must fall is given by this, that the potential must fall faster than the Coulomb potential, that the potential, if it falls faster than 1 over r as r tends to infinity, then our method will be applicable. For those potentials which go as 1 over r, specifically the Coulomb potential, somewhat different techniques have to be used, okay, and some of our analysis is not applicable to it directly, it has to be modified. One has to introduce what is called as the Coulomb phase shift, okay, that requires different techniques, and we will not have the time to discuss that, but you know this is nicely discussed in most books on quantum mechanics like Schiff's quantum mechanics or Landau and Lifshitz are good sources. One of our master's students, Renu Mathai, had a very good report on the continuum eigenfunctions of the Coulomb potential, so that copy should also be available in our lab. You can go through it, in which the Coulomb problem is discussed in great details, but we will restrict our discussion to those cases, those potentials which do go to 0 as r tends to infinity, but at a rate which is faster than the Coulomb potential, which is faster than 1 over r. So it is 1 over r to the power 1 plus epsilon, epsilon could be no matter what, how small, but it must be greater than 0, okay. If it is 0, this method is not going to work. It could be small, as long as it is small it will work, and in this case, since f is nearly constant, you can write the solution as a superposition of e to the ikr and e to the minus ikr. This is a superposition of spherical ingoing waves and spherical outgoing waves. You can do that, but instead of writing this as a superposition of spherical ingoing and outgoing wave, you can also write it as a superposition of sine and cosine functions. It does not matter, because a function you can represent as a superposition of linearly independent pair of functions, and as long as the basis is complete you can use any basis set. So you can use either spherically ingoing or outgoing waves, you can use the Bessel function and the Neumann functions, or you can use the Hankel functions of the first kind and the second kind. So there are alternative basis pairs that you can use, and here I have written this instead of the exponential functions as a superposition of cosine and sine functions, and once you have it you can easily write it as a sine of kr minus l pi by 2 and add a phase shift here, because sine a plus b is sine a cos b plus cos a sine b, and you get the previous form directly, right. So instead of the constants C1 and C2 you have two other constants which are a and delta, and you can get one as the tan inverse of the ratio of the other two terms. So it is a straightforward thing to do, and what you discover is that your radial function, which is y divided by r, is simply this sinusoidal function, which is the same thing as you get for a free particle with an additional phase shift, and you can write this sinusoidal function again in terms of spherical outgoing waves and spherical ingoing waves, and this is the form that we have used in our analysis in our previous class, okay. So the phase shift does not come out of the blue, it is directly a consequence of the scattering potential. Nevertheless, there are certain conditions that the potential must satisfy, and in particular this method does not work in the case of the Coulomb potential. Somewhat different techniques are to be used, but for most other potentials and most of the physical potentials that you work with are not exactly 1 over r potentials, because there are other electrons and screening and so on, okay. So in other cases you find that this is a fairly good approximation, and the radial function is then given by in terms of the spherical ingoing and outgoing waves, and this is the form that we used to write the total wave function, and this pretty much completes our analysis that we did in our previous class. I will go through some of the essential steps just to reinforce the point that you had the total wave function, which was written in terms of the spherical harmonics and the Bessel functions with appropriate boundary conditions, and here there is a phase shift delta coming due to the potential, and then these CLM, these were the unknown coefficients, but then in these two forms this is the phenomenological expression, this is the total solution to the H psi equal to E psi Schrodinger equation. These two solutions must be equal, and they must guarantee that the coefficients of the outgoing waves are equal. This coefficient involves CLM, but this we have already used earlier. we obtained this CLM explicitly in our previous class. So now you can set these coefficients equal. So you get the coefficient of the outgoing wave e to the ikr. Over here you will get the ak, you will get the sum over il 2l plus 1, you have this e to the minus I l pi by 2 which is coming here, you have got the 1 over 2 ikr which is here, you have got the Legendre polynomial, and then from this term you have got the scattering amplitude and the 1 over r, right. So this is the term which multiplies the spherically outgoing wave in this form, and in the lower form you have got an exactly, you do the same thing, extract the coefficient of e to the ikr, in which you also have CLM. So you plug in this CLM from the result that we had obtained in the previous class, and now all you have to do is to equate this with this, okay. Those are the two coefficients of the spherically outgoing waves. So once you equate them and then you cancel common terms, simplify, and essentially you get the Faxen-Hallsmark scattering amplitude, because you have the scattering amplitude over here, you move this term to the right and you get this e to the 2 I delta l minus 1 over 2 I k, which is the scattering amplitude, okay. So it is a very simple analysis, and this is sometimes referred to as a partial wave method, because there are so many partial waves with different L quantum number which contribute to the scattering amplitude. There are infinite of those, because L goes from 0 to infinity. The linear momentum is a good quantum number for free particles, but angular momentum is not, and therefore you need a superposition of the entire basis which includes L going from 0 through infinity, and it would be a very burdensome computation if you really had to do all of these infinite partial waves. But you do not really have to, because as L increases, the radial function of the continuum, the radial part of the continuum function will go as r to the power L, and it will not be able to penetrate into the core, into the scattering region. So only a few partial waves have to be considered, and we have done calculations in which just about 8 or 10 partial waves L equal to 0 up to L equal to 8 or 10 are sufficient. Sometimes you need more than that, you can take 10, 20, 50, 100, people even do 1,000, but certainly not infinite, and even 1,000 is a tangible number, okay. It is not something which is not manageable, and the centrifugal barrier is the main reason that you can truncate this partial wave expansion to a certain limit. Okay, now we are going to get the boundary conditions, and we will see how these boundary conditions are recognized. We have already been discussing these boundary conditions, we have already used these boundary conditions, but we will discuss them further to recognize a particular element in the boundary condition which is of importance. And to be able to do that, we first write the incident plane wave, which is this, in an equivalent form over here, okay. This is completely equivalent form, but I will demonstrate very quickly how this is, these two forms are equivalent. And once we do that, we will write the total wave function also in a form which is similar to this second form, and then we shall proceed to discuss the boundary conditions, and these boundary conditions are different for collisions and for photoionization. Our eventual goal in this discussion is to relate the boundary conditions for photoionization and collisions, and we have already seen in some of the diagrams that I have discussed earlier that they both have the same final state, but the initial states are different, and there is a certain time reversal symmetry which is involved which connects the two. So that is our goal for this discussion. We will get to that, and to be able to get to that, we first want to write the total wave function also in a form which is similar to this second form. So let us write that. So this is hung up a little bit, okay. All right. So this is your incident plane wave, this sinusoidal function you write as e to the ikr and e to the minus e to the plus I theta e to the minus I theta divided by 2I, and this I to the L you write as e to the IL 2 pi by 2, okay. So that you can multiply both of these terms by e to the IL pi by 2, that will cancel this e to the minus IL pi by 2, and here you will get e to the IL pi by 2 into e to the IL pi by 2. So you will get a e to the IL pi in the second term, right. So that is what you have got, minus 1 to the L, because e to the I pi is minus 1, right. So now you have got the incident wave, which is a plane wave, which is written in terms of these Legendre polynomials, and you have got this spherical outgoing wave, a spherical ingoing wave, which is multiplied by minus 1 to the L, and if this minus 1 to the L, you take this PL cos theta and multiply both of these terms by PL cos theta, you have got PL cos theta into minus 1 to the L. What is PL of minus cos theta, right. Okay, so that is what it is. You have got the Legendre polynomial for minus cos theta over here. So this is your incident wave. So you have got PL cos theta into the ikr and PL of minus cos theta into e to the minus ikr. And now let us write the total wave function in exactly the same form. This is also written as PL cos theta into the ikr, but now we know that the total wave function must have the scattering phase shift delta L. The coefficient of the e to the minus ikr again is PL minus cos theta, it is exactly the same as we know, except that there is an additional scattering phase shift. So that goes over here, okay, right. But then you do not know what CL is. This is the unknown coefficient in the total wave function. The question is, how do you determine CL? What is the boundary condition which gives you the CL? Okay, this is the unknown, this is what you have to find out. Now we do know that the total wave function is the sum of the incident wave and the scattered wave, right. So you have got the incident wave, you also have the total wave. So if you subtract the total wave from the incident wave, you must get the scattered wave, and that condition will give you what CL must be. Now you know what the scattered wave is. Scattered wave is known, is it not? This is the scattered wave, it is e to the ikr over r multiplied by the scattering amplitude. We have just determined that, right. So now tell me what CL should be, because all you have to do is to subtract this incident wave from the total wave to give you the scattered wave. You have got all the pieces, now tell me what should be the value of CL. Got it? One. You should get it just by observation.
1.
If you were listening. What should be CL? What value of CL will give you the scattered wave?
1.
It can't take that time, come on.
1.
If you just look at one of the terms, you will get it. You don't even have to see.
1, right?
You want to remove this part. What is it? You got PL cos theta e to the ikr.
E raised to I delta 1.
Come on.
E raised to I delta n, man.
I think you're not even trying. It is very.
E raised to I delta n.
Legendre function.
E raised to I delta n.
4 pi by 2 L plus 1.
No.
E raised to I delta n.
It is too simple.
It's 1. It's 1.
If you look at any one of these terms, there are two terms. Okay, how do you subtract this term from this term to get this? This one has nothing in e to the minus ikr, right? All you need is put CL equal to e to the I delta L. That is all you need to do. Okay. If you put C equal to e to the I delta, that is it. Do you see it? You are not even trying, I am afraid. Yeah, it is taken care of. You got e to the minus I delta L here. So that is what gives you this e to the 2 I delta L, right? Okay. So this is a beautiful result, that the choice of this coefficient, and this is an extremely important choice, because this is what determines that the process you are talking about is a collision phenomenon. We know that the answer is a collision scattering amplitude, right, which is what gives you the Faxon-Holzmark scattering amplitude, right, and you get it by choosing CL to be e to the I delta L. CL are, you know, until we recognize it to be this e to the I delta, it is just a multiplicative factor in the superposition, right. It is an arbitrary multiplicative factor, but it no longer remains arbitrary. What is it that pins it down? It is the boundary condition that the solution will give you the scatterings, the solution to the scattering problem, which is the sum of this incident plane wave plus a spherical outgoing wave scaled by 1 over r and an angle dependent scattering amplitude. That is the boundary condition, and this choice is completely equivalent to C being e to the I delta. Okay. Now notice that this will also, the value of C will also affect the normalization. Okay. So when you make this choice, you often say that you have normalized the solution according to outgoing wave boundary condition, okay, because that is what you have in your scattered part. In the scattered part you have got a spherical outgoing wave, okay, that is the only thing you have got in the scattered out part of the function, okay. There is no ingoing component in the scattered wave, which is why this is called as a normalization according to the outgoing wave boundary conditions. So this is the normalization according to outgoing wave boundary condition, and you have got the scattering phase shift, which we know is coming from the potential itself. Okay. Now let us look at this solution further. This is our total wave function, and we will put in the value C equal to e to the I delta L in this, and with this you have got this total wave function, which is given as this e to the I delta L will give you this particular solution. And let us write it together with the time dependent term, because that is more interesting to see, because the net wave function must be multiplied by this e to the minus I omega t. That is the thing which tells you whether the wave is a travelling wave, whether it travels from the left to the right or right to the left, okay, from the center to farther away or in the other direction. So when you put in this e to the minus I omega t, you get kz minus omega t from here and kr minus omega t. So you recognize this as a plane wave and this as a spherical outgoing wave. So this is the picture that we have been using everywhere, and this picture now really makes sense because it shows how a surface of constant phase propagates. Okay. This travel is of importance. This is what tells you what is the nature of the solution. Without the time dependence, actually it does not mean anything. E to the I k z is not necessarily a function which is moving along the plus z axis. Okay. What determines is what is dz by dt. Is dz by dt positive or is it negative? If it is negative, it would actually be a wave which is going in the negative z direction. Okay. So likewise, e to the I k r by itself does not determine that it is a spherical outgoing wave. The argument with reference to time is k r minus omega t, so that the surface of constant phase will be given by k r minus omega t being a constant, and that will require dr by dt to be given by a positive number. And since dr by dt is positive, you have got the radius of the surface of constant phase which increases. That is what makes it a spherical outgoing wave. Okay. So now our solution is complete, inclusive of the time dependent term, and what gives us this correct form is the choice C equal to e to the I delta, and this is of tremendous importance in our discussion for photoionization. Okay, so this is what is called as normalization as per outgoing wave boundary condition. This scattering phase shift gives you a coefficient which describes the collision phenomenon, and the question that we are going to ask now is what boundary condition will describe photoionization. We know that Cl equal to e to the I delta L will describe the collision. How should C be chosen so that we describe photoionization? That is the next question we want to ask. We know that there is a certain similarity. We know that both of these processes have got the same final state, but different initial states, even the initial ingredients are different. So now let us begin to look at the photoionization event, in which, as I discussed earlier, you have got a photoelectron in the final state. So you have got a certain central region, an atomic system, a quantum atomic system, which has absorbed electromagnetic radiation, an electron has been knocked out through the photoelectric effect, is goes into the continuum, and you sense it in a certain detector, and this direction in which the photoelectron has escaped is unique. Okay. So the exit channel has got a unique direction. In the collision it was just the opposite. In the collision you had a scattering center, you had the electron gun at one place, and this electron gun fired electrons toward the target. So this entrance channel was unique. Okay. So in photoionization it is the exit channel which has got a unique direction, and if you see that if you were to take a picture of this process and imagine this being recorded on a film, this process would be somewhat similar to a film which is being run backward in time. Okay. So it suggests to you that it has something to do with time reversal symmetry, and we now need to discuss what is meant by time reversal symmetry in quantum mechanics and how does it connect the solutions of photoionization to collisions. Okay. So there are, symmetry plays an extremely important role in all physical phenomena and of course in atomic processes as well. We first dealt with the rotational symmetry. Okay, the generator for rotations are the angular momentum operators, they give us the SO3 algebra, right. Then we also discussed the dynamical symmetry of the hydrogen atom coming from the SO4 symmetry, right. Then there is parity, and parity is also important in atomic processes. You have seen the dipole selection rules as an application of the Wigner-Riccard theorem. You know that dipole transitions take place only when parity changes. Okay. So there are these parity selection rules which are of importance, but then there are many other symmetries, and typically a symmetry is an operator which you can write as 1 minus I over h cross epsilon g, and when G is a Hermitian generator of the symmetry gamma. Okay, that is the typical interpretation of a symmetry operation, because it gives you a gamma, an operator which commutes with the Hamiltonian. So, the Hamiltonian remains invariant under that operation. That is the idea of symmetry. Okay. So, now the dynamical symmetry we have discussed at length in unit 1. So far as the geometrical symmetries are concerned, you have the translational symmetries generated by the linear momentum, which is conserved in translationally homogeneous space. You also have the angular momentum, which is the generator of rotational rotations, and these are, as you can see from both of these operators which generate the corresponding translations or rotations, these are unitary transformations. They are also continuous transformations. In homogeneous space you can move it infinitesimally. This is the generator tau delta x is the generator of infinitesimal translation. U delta phi is the generator of infinitesimal rotations. Okay. So these are continuous variables, but then there are discrete symmetries like parity and time reversal. These are discrete symmetries. In parity you go from one space into the other, which is the mirror space, right, and you do so in one shot. Time reversal is again a discrete symmetry, because from a certain time t you go to minus t, there is nothing in between. It is not like a number 0.5 on a real number axis which you reduce to 0.4, then to 0.3, to 0.2, 0.1, 0, and then minus 0.1 and so on. You do not do so continuously. You do this with angles, you do these with translations, but you do not do it with time reversal nor with parity. So these are discrete symmetries. Just like charge conjugation, you go from the electron to the positron, there is nothing in between. So this is a discrete symmetry, and you know that parity is violated in the electroweak interaction, the weak interaction, and beta decay it is violated, right. And since electroweak force is the same force, atomic processes being governed mostly by electromagnetic phenomena, but then the electromagnetic interaction is not different from the weak interaction, you would expect parity to be violated in atomic processes as well, because it is the same interaction, right. And yes, there is a quest for parity violating phenomena. Many have been observed in atomic physics, and we will not have time to discuss those aspects in this part of the course. Our focus here is on collision and photoionization. Then there is this charge conjugation as well as the time reversal. Our interest is in relating these two phenomena and how the time reversal symmetry connects solutions of collisions to the solutions of photoionization. That is our focus in the present discussion. But then remember that Cp violation has been observed, and if Cp is violated, time reversal symmetry also ought to be violated, and you can look for that in atomic physics also. Okay. And if it is violated in atomic physics, where will you find it? You will find that you will have these electrons to have a certain dipole moment. So you can look for the dipole moment, and if you find it, it would be an evidence of the breakdown of the T symmetry, and that would be wonderful. This is experiment will be much cheaper than what it is at the Large Hadron Collider. Okay, you can do it in a lab, and people are looking for this. They do it not just for atomic systems, but actually for molecules, because there is a certain enhancement factor which enables which gives you some comfort, because the probability of detection goes up very much because of that. Cp violation is of importance. Some of you keep wondering where is all the antimatter, and part of the reason you do not find as much antimatter as you find matter is because of Cp violation, but that is again an involved question which does not fall into the scope of our discussion. We will nevertheless need to understand what exactly is meant by time reversal symmetry, okay, and it is not the same as in classical mechanics. So let us first understand what time reversal symmetry means in classical mechanics. So classical equations of motion are symmetric with respect to t going to minus t, and what this means is that if you have a particle 1 which is at position vector r1 and momentum vector p1 at t equal to 0, and if there is an identical particle, this is particle 2 whose position at t equal to 0 is the same as the position of particle 1 at t equal to 0, but its momentum is opposite, okay, its linear momentum is opposite. Then if these relations hold, that at a later time the particle 2 will have the same position as particle 1 had at a previous as much time, okay. So this is t going to minus t. So at a previous as much time, if the second particle has the same position as the first particle had at as much previous time, and the momentum is the negative of what the first particle had at that much previous time, which is minus of p1 minus 2, then you say that motion has time reversal symmetry. This is the meaning of time reversal symmetry in classical mechanics, and in classical mechanics it is very easy to deal with, because this is a picture which shows you how the definition which I just provided, this is the position of these two particles, particle 1 and particle 2 at t equal to 0, and these are the momenta of these two particles at t equal to 0, except that the momentum of the second particle is opposite to that of the momentum of the first particle, and this is the criterion for time reversal symmetry. This diagram is from a very nice article by Domingos. I will strongly recommend this article, in which he discusses time reversal in classical mechanics and in quantum mechanics, okay. So classical equations of motion are symmetric with respect to t going to minus t, because both r of t and r of minus t are solutions to Newton's laws, to Newton's equation of motion, and also to Lagrange's. Both are second order differential equation, right. So d2 by dt2 as t goes to minus t remains the same, okay. Same thing happens with Lagrange's equations. Hamilton's equations are first order equations, but then there is a minus sign here, okay, so that takes care of it. So all classical equations, whether Newton, Lagrange or Hamilton, they are of course equivalent to each other, so no wonder, but it is obvious that they are symmetric under time reversal, t going to minus t. The question is, what does time reversal symmetry mean in quantum mechanics, where the evolution of the system is described not by Newton's equations or Lagrange's or Hamilton's equations, but by the Schrodinger equation, and this is the rate equation. Del psi by del t tells you how the system evolves with time, okay. So what is time reversal symmetry in quantum mechanics, and this is what we will discuss in our next class, and then connect the solutions to collisions and photoionization. So that will be our point of discussion for the next class. We do expect the solutions for photoionization to be related to the solutions of the collisions experiment, because they have the same final state. You can see it from these two diagrams that we have discussed earlier, and this relationship is actually what connects the collision boundary conditions to the photoionization boundary conditions, and the connections will emerge from the time reversal symmetry in quantum mechanics. So with this I will conclude today's class. Essentially the question boils down to, how do you choose the normalization? CL equal to e to the I delta L is what gave us the correct boundary condition to describe the collision process. So the question is, how are we going to choose CL to describe photoionization? So that is the question we are going to answer. There are a few references, most of this discussion is from Fano and Rao, It is a very nice book, and there are some other sources which I have suggested over here. If there are any questions, I will be happy to take, otherwise we proceed from this point in the next class.